What do you do when there's no nice antiderivative? The antiderivatives of some functions, like sine of x squared, 1 over the natural log of x, and the square root of 1 plus x to the fourth power, have no elementary formulas. When we cannot find a workable antiderivative for a function f of x that we have to integrate, we can partition the interval of integration, replace f of x by a closely fitting polynomial on each subinterval, integrate the polynomials, and add the results to approximate the definite integral of f of x. This is an example of numerical integration, or approximate integration. There are many methods of numerical integration, but we will study two here, the trapezoidal rule and Simpson's rule. So let's start off with trapezoidal approximations. As the name implies, the trapezoidal rule for the value of a definite integral is based on approximating the region between a curve and the x-axis with trapezoids instead of rectangles. Assume the length of each subinterval is delta x is equal to b minus a over n. Then the area of the trapezoid that lies above the x-axis in the ith subinterval is t sub I, which is equal to delta x over 2 times y sub I minus 1 plus y sub I, where y sub I minus 1 is equal to f of x sub I minus 1 and y sub I is equal to f of x sub I. Then the area under the curve and above the x-axis is approximated by the sum of the trapezoids. So just as a quick reminder, here we have this trapezoid. And the way that you find the area of a trapezoid is you multiply the width, which in this case is delta x, by the average of the heights. And so in this case, this height we would call y sub 0, and then this height here is y sub 1. So for the very first trapezoid, if I wanted to calculate the area of this trapezoid, we call it t sub 1. That would equal delta x over 2 times y sub 0 plus y sub 1. And that would represent the area of the very first trapezoid. And now what we want to do is we want to calculate t, which represents the sum of all of these trapezoids' areas. So this would be equal to t sub 1 plus t sub 2 plus all the way to t sub n. And we just calculated t sub 1. So let's expand that out. We said t sub 1 was equal to delta x over 2 times y sub 0 plus y sub 1. And then t sub 2, or the area of the second trapezoid, would be delta x over 2 times y sub 1 plus y sub 2. The area of the third trapezoid would be delta x over 2 times y sub 2 plus y sub 3. And then this pattern would continue on, and the area of the very last trapezoid, if we have n of them, would be delta x over 2 times y sub n minus 1 plus y sub n. Now notice that in this summation, every term has delta x over 2, so we can factor that out of our sum. What's going to be left over? Well, if you notice, every single y value is repeated twice, except for the first one and the last one. Why is that? Well, if you look at our picture here, the first height and the last height are the only ones that are not shared by two trapezoids. That's because they're on the ends. But for example, the next height and every one after that is shared by two different trapezoids because they're not at the very ends. So when I'm writing out my summation, I'm going to have y sub 0, and then every other y value except for the last one is going to have a duplicate. So I'm going to have plus 2 y sub 1 plus 2 y sub 2 plus dot 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 plus 2 y sub n minus 1 plus y sub n. Now there's a few different ways I could notate this. Maybe I'll have delta x over 2 still factored out, and instead of having the y values, these y values are the same as the x values if we plug them into our function. So y sub 0 is the same thing as f of x sub 0. And then plus, I'm going to add the very last term. And then all the other terms, I can condense that into a summation. So this would be 2 times the summation from I equals 1 to n of f of x sub I. Oops, the upper index should be n minus 1. And that is one way that we could condense that there. So here's the formal formula for the trapezoidal rule. It says that the definite integral from a to b of f of x dx is approximately equal to t sub n, which means we are using the trapezoidal rule with n subintervals, and t sub n is equal to delta x over 2 times f of x sub 0 plus 2 times the other f of x sub i's until the last one where it's just a single f of x sub n. And delta x is equal to b minus a over n, and x sub I is equal to a plus I times delta x. And we've seen both of these definitions before, so the trapezoidal rule, that t sub n is just the new one. And we've also seen this type of notation before when we've used the midpoint rule, so we've had m sub n. When we use the left endpoints for a Riemann sum, we used L sub n, and when we use the right endpoints for a Riemann sum, we've used R sub n. So this type of notation is not new either. Example 1 says, use the trapezoidal rule with n equals 4 to estimate the definite integral from 1 to 2 of x squared dx. Compare the estimate with the exact value. So if we are wanting to use trapezoidal rule with n equals 4, that's another way of saying we are wanting to calculate t sub 4. So let's do a couple things. Let's calculate delta x first. So delta x is equal to b minus a over n. In this case, b is 2, a is 1, and n is 4. So if you simplify that, that ends up giving us 1/4. So that means that we're starting at 1, so our x sub 0 is 1. Then our next x value, we would add the delta x value, so 1 plus 1/4 is 5/4. X sub 2 is our next x value, so we'd add on our delta x value again. That would be 6/4 or 3/2. And then x sub 3 is equal to 7/4. And then x sub 4 is equal to 8/4, which is also equal to 2. And we expected that because that's our b value. So we start with our a value, and we end with our b value. So why do we care about these x values? What are we doing now? So if you follow the formula, t sub 4 is equal to delta x, which delta x we found was 1/4, and then we're dividing that by 2, and then we're evaluating our function at f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 times f of x sub 3, and then plus f of x sub 4. I'm going to go ahead and plug in the x values and replace those. Okay, so I've gone ahead and I've replaced the x values. Now what we want to do is we want to actually plug these in to our function. And remember, our function in this case is f of x equals x squared. So if I squared 1, if I plug that into my function, 1 squared is just 1. Then I'd have 2 times 5/4 squared would be 25 over 16. 3/2 squared would be 9 over 4. 7/4 squared would be 49 over 16. And then 2 squared is 4. So if you simplify this number, it should come out to the value of 75 over 32. So that is t sub 4. The second part of the question wanted us to compare the estimate with the exact value. So let's go ahead and clean up our screen, and then we'll find the exact value of the definite integral that we started with. Okay, so we have our approximation from when we calculated t sub 4. Now we want to find the exact value, so I'm going to integrate x squared dx, and the antiderivative of x squared is x cubed over 3. and I'm evaluating this from x equals 1 to x equals 2. So we have 2 cubed over 3 minus 1 cubed over 3, which is equal to 8/3 minus 1/3. And that is equivalent to 7/3. So our approximation was 75/32, and our exact value was 7/3. And it asks us to compare, and so one way that we could do that is we can look at the difference between the two numbers. So I went ahead and I subtracted the two numbers, I simplified and got the fraction 1/96. So what that means is t sub 4 is an over-approximate, or over-approximation of the integral from 1 to 2 of x squared dx by 1/96. So that's a pretty good approximation, especially since we only used 4 trapezoids. In the next video, we're going to be talking about what's another type of approximate integration that we could do using something other than trapezoids. And also, as we saw, it seems like trapezoids are better for approximating because, if we have some kind of curve, and before we were using rectangles, and the thing about rectangles is they don't account for kind of the curvature, and now that we're using trapezoids, the trapezoids are kind of better accounting for the curvature, and so it's leaving less blank space or empty space, if you will. So in the next video, we'll use a different kind of approximation.